When you establish this connection, the phone and charger begin a digital handshake. Your device requests a specific power profile to begin the charging cycle. Behind your wall outlet sits alternating current at 120 or 230 volts, a high-voltage oscillating stream that would destroy a smartphone battery if applied directly. The engineering challenge is stepping that voltage down to approximately 5 to 20 volts instantly, ensuring the energy is compatible with the battery's internal chemistry. Fast charging is a process of formatting raw electrical current into a regulated, low-voltage supply. One way to lower voltage is through resistance, placing a physical barrier in the path of the current to reduce the flow. Because energy must be conserved, electricity blocked by this barrier converts into thermal energy. If a charger used simple resistance to step down 60 watts of power, the thermal output would be high enough to deform the plastic casing of the charger block. This method is inefficient because it discards a significant portion of the electricity drawn from the wall as waste heat. To increase power without increasing temperature, engineers had to abandon the model of resisting current. The alternative is the silicon transistor, which acts as a high-speed switch rather than a bottleneck. Instead of partially blocking the current, the transistor exists in two states. It is either completely open or completely closed. When the transistor is open, electricity flows through with almost no resistance. Because there is no friction to fight, very little heat is generated. When the switch is closed, there is zero flow, which also prevents heat generation. By alternating between these two states, the charger circumvents the thermal buildup caused by traditional resistors. These silicon transistors operate in incredibly rapid cycles, opening and closing hundreds of thousands of times per second. This process is called pulse width modulation, and it allows for precise control over power delivery. Instead of weakening electrical pressure, the charger modulates the width of these energy pulses. The duty cycle describes the ratio of time the switch is on versus total cycle time. Wider pulses deliver more average power, while narrower blocks decrease output. This allows the charger to ration energy with microsecond precision, adjusting the flow based on the phone's immediate needs. However, a chemical battery cannot be charged directly with these rapid, high-voltage pulses. To prevent damage to the lithium cells, the energy must be converted back into a steady, continuous stream of direct current. The charger passes the pulses through a filter composed of inductors and capacitors, which act as an energy reservoir. These components absorb the energy from the pulses and release it as a smooth, continuous stream. The filter averages the rapid switching of the transistor into the exact stable voltage the phone requires. High-voltage wall power is segmented by a high-speed switch, regulated by the duty cycle, and leveled out by an energy reservoir. This high-speed switching allows the device to process significant wattage, while the exterior of the charger remains cool to the touch. By replacing constant friction with high-frequency switching, engineers can deliver higher charging speeds without the destructive consequences of waste heat.